In this appendix to Chapter 1, we'll look at time value of money calculations. TVM is probably the most fundamental concept in finance. It's particularly important in personal financial planning as it forms the basis for finding how much we need to save for our child's college education, a new house, or our retirement. How much house can we afford? What's the payment going to be on that car we're thinking about? How much we should pay for an investment opportunity. As we covered in Chapter 1, an interest rate is the cost of money. Using TVM, we can answer the questions on the slide. If I deposit $10,000 today, how much will I have for a down payment on a house in 5 years? Will $2,000 saved each year give me enough money when I retire? How much must I save today to have enough for my children's education? The basic TVM theory is that a dollar today is worth more than a dollar received in the future. Bird in the hand is true. Why? If I had the dollar today, I could invest it and have more than a dollar in the future. A dollar in the future is uncertain. Here are the topics we'll cover in this appendix. If you've watched the 2 videos on the TI Business Analyst 2 Basics and the TVM case, then you're ready for this material. We'll cover 4 types of problems that arise frequently in personal financial planning. Simple interest, future value, present value, finding a loan payment. We'll cover 4 methods of solving these problems. Formulas. You probably won't actually use the mathematical equations, but they give you a sense of what your answer should look like. TVM tables. Rarely used anymore, but we'll look at them briefly. Our focus will be on the last 2 methods. Financial calculator, specifically the TI Business Analyst 2 Plus, and Excel. These last 2 are the ways most of you would use in solving TVM problems. As we go through these examples, I recommend you work the problems in your calculator to be sure you're comfortable using them for the TVM problems. First, let's be clear in our definitions. Future value is the amount a sum will be worth in the future if invested at a given interest rate. It's called compounding, and this is the secret to making your money grow. Present value is the current value of an amount to be received in the future. This is called discounting. Future value is the most intuitively comfortable. It's what you'll have in your savings account if you put X dollars in now and earn R interest rate per year for N years. Present value is a bit harder to wrap your head around, but it answers several valuable personal and corporate finance questions. If I want X dollars in 5 years and I can invest at R interest rate, how much do I have to deposit now? If I want X dollars in 5 years and I can invest at R rate, how much do I have to deposit each month to reach that goal? To begin with, we won't be using payments or the PMT key on your calculator. PMT is for annuities, repeating amounts. We'll begin our look at TVM with lump sums, a single amount. The sign convention is important when solving TVM problems with your calculator or Excel. The sign convention applies to dollar input amounts, which are the present value, payment, and future value. The other 2 inputs are the interest rate and the time period. Think of the cash flows relative to you. Money coming to you are inflows, and they're positive. Money going out from you, whether paid out or invested, are outflows, and they're entered as negative values. Either PV or FV must be negative in both your calculator and in Excel. It's important to point out that there are many different ways to refer to the interest rate that we use in time value of money calculations. Students often get confused with the terminology, especially since they tend to think of an interest rate only in terms of loans and savings accounts. Note that interest rates are percentages, but are represented differently in Excel, in formulas, and in your calculator. In Excel and in formulas, 12% is 0.12. In your calculator, 12% is 12. Time periods. Time periods in TVM calculations are expressed in years, so 3 months is a quarter of a year. It's 0.25. Very important. The interest rate and the time period must match. We think of the time periods, as in the tables, as being years, but they don't have to be. This is usually kind of a least common denominator type situation. Depositing $50 each month for a year is not the same as depositing $600 at the end of the year. Why? Interest earned on the $50 each month accrues. If the interest rate is given as an annual rate, but deposits are made monthly, then the rate has to be converted to a monthly rate to match the period of the dollars. It may help to visualize the cash flows in a TVM problem represented on a timeline. As the slide states, the tick marks are the end of a period. Time 0 is today. The sign convention is repeated at the bottom. When we use the term cash flow, we're implying that the dollar values are different each period. Using the term payment refers to an annuity where the cash flows are the same every period, as we'll see as we work through the examples. The upper timeline represents $100 to be received in 2 years. The lower timeline shows a 3-year $100 annuity. This is an uneven cash flow stream where each period's cash flow is a different value. This is more common in corporate finance than personal finance. Many TVM problems are straightforward, so no timeline is really necessary. But in more complex cases, drawing a timeline to visualize when the cash flows occur can be very helpful. We'll look at 2 types of TVM problems from both the present value and future value side. A single amount could be received in the future or invested now. In either case, PMT is 0. An annuity is a finite series of equal payments that occur at regular intervals. Key words in this definition: finite, it's a specific number of periods. Equal, the payment amount is the same every period. Regular intervals means the payments always occur on the same schedule, every week, every month, every year. With annuities, the sign convention is very important. Simple interest, which we don't see much anymore. It's simply the dollar amount times the rate times the number of years. We're primarily interested in the future value and present value formulas. Now, I do not anticipate that you'll use the formulas, but I do want to show them so you have a feel for what your answer to a problem should be. The present value of a future value amount is smaller than the future value. If you looked in those tables, the table value is less than 1. The future value of a current value is greater than the present value. The table value will be greater than 1. I'm using the Texas Instruments Business Analyst 2+. Other calculators are similar. Before we start, let's make sure our calculator settings are correct. Future value is a dollar amount. Positive if an inflow to you, negative if an outflow. Present value is a dollar amount. Positive if an inflow to you, negative if an outflow. IY is the interest rate per period. N is the number of periods. Payment is an amount deposited, which will be negative, or withdrawn, which means it comes to you, it'll be positive. Periods per year must be set to 1. To check this, press the second and P/Y key. If the value displays as 1, then you're good to go. If not, enter a 1 and press enter, and then second and quit. As already mentioned, the interest rate in your calculator is entered as a whole number. 5% is entered as 5. Data entered in the calculator cells stay unless they're cleared out or overlaid. Make sure to clear the TVM registers after finishing a problem or before starting a problem. With the TVM keys, since we only have 5 keys, you can enter data in 4, even if 1 is 0, and compute the 5th. It is important to point out that clear TVM clears the future value, present value, N, IY, and payment registers. If not cleared or overlaid, the last data remains in the register. C/CE and clear work do not affect the TVM keys. Clicking on the Excel logo will bring up a worksheet with the appendix examples solved in Excel. Click on the tabs at the bottom of the worksheet to move between examples. Excel has a function that corresponds to each of the TVM keys on your calculator. Though very uncommon today, we are going to look briefly at simple interest. Simple interest has 3 components: the principal, the amount invested or saved, rate, the annual rate of interest, and time, the length of time the money is invested or stays on deposit. This is example A on page 32 and 33. The principal is $1,000, the rate is 5%, so it's 0.05, time period is 1 year. So the interest owed is $50. Example B on page 33. The principal is $750, the rate is 8%, and the time is 9 months, or 0.75 of a year. So the interest earned is $45. Let's start looking at how to solve these problems in your calculator. Example B again. N is 0.75, 9 months. IY is 8 8%. PV is a minus 750. Use the plus or minus key. You deposit 750. Enter 750, then press the plus minus key at the bottom, and then hit PV. Payment is 0. You're not adding anything to your initial deposit. To solve for future value, press Compute and FV. You'll get $794.56. So your interest minus the initial $750 is about $45, $44.56. There's an important difference between using a formula and using a financial calculator or Excel, the sign convention. In Excel and in your calculator, either the present value or the future value must be negative. In this case, you invested $750 at time 0, so that's an outflow from you. It's negative. To enter a negative in your calculator, do not start with the minus sign. Enter the numeric value, in this case $750. Then press the plus or minus key in the lower right of the keypad. This is a toggle switch. It changes the sign back and forth. When minus $750 shows in the display, then press the PV key. Moving along, let's look at the future value of a lump sum, compounding. This is the concept that grows your money when you invest it and leave it invested. This slide shows 4 potential solution methods. We're going to look at all 4 for each example, but I expect you to be able to use the calculator and Excel. Example C on page 33. As shown, suppose you invest $1 for 3 years at 10%. Using the formula, 10% becomes 0.10. N is 3, so the future value is 1.331. You can find this in your calculator by entering 1.10, press the Y raised to the X key, 3 equals, and multiply times 1. Note that our result using the formula with a dollar investment is the same as the table factor, 1.331. Continuing example 3, using your calculator. N is 3, IY is 10, PV is a minus 1, remember, enter 1 plus or minus. Payment is 0, we're still dealing with a lump sum. Solve for future value. Compute FV, 1.331. Excel has a function that matches each of the gray keys. That future value function is shown on the slide. Remember that IY in Excel is a decimal, so the 10% is 0.10. As with your calculator, either present value or future value must be negative. This table from the text recaps 3 of the 4 methods we just covered. It's on page 33. Example D, page 34, brings up the issue of matching period and interest rates. The interest rate is quoted as an annual rate, an APR, but is compounded monthly. You need a monthly rate. Fortunately, an APR is just the periodic rate multiplied times the number of periods in a year. In our case, that means we can find the periodic or monthly rate by dividing the 12% by 12 months, 1% a month. If the rate is monthly, then the periods must be monthly as well. The period is given as 18 months. So using the formula or the tables, I is equal to 0.01 or 1%. Number of periods is 18. Continuing example D, using the periodic rate and the number of periods, carries over to our calculator and Excel. N is 18, IY is 1, present value is a minus 400, payment is 0, future value is 478.46. This table recaps 3 of the methods used to solve example D, and it's on page 34. Continuing future value calculations, we move from valuing lump sums to annuities. The definition of an annuity is shown on the slide. Equal deposits or withdrawals at equal intervals earning a constant rate. The equal deposits or withdrawals are where we use that PMT key. Examples include retirement savings or any other savings goal in which you deposit an equal amount at equal intervals. Another example would be a car payment or mortgage where equal payments are made on a regular basis for a number of periods. As before, this slide shows us 4 ways to calculate the future value of an annuity, and we'll cover all 4 on the coming slides. Example E on page 34. 3 $1 deposits made at the end of the next 3 years, earning 10% interest. Notice again that the formula solution using a dollar amount yields the table value. The sign convention becomes even more important with annuities. In this case, the equal amount is the deposit. It's an outflow, so payment is negative. Again, a recap of 3 of the methods for solving for the future value of an annuity. This is on page 34. Example F, page 35, just extends our annuity example to amounts greater than $1. To enter this formula directly in your calculator, you'll need to use the y raised to the x key, which raises the value y to the power x. You would enter 1.08 y to the x 10 equals minus 1 divided by 0.08 times 40. You'll get the 579.46. Continuing example F, the setup in your calculator and Excel are the same as those we've previously looked at. N is 10 years, IY is 8.08 in Excel. Present value is 0. You're not starting with any money in the account. PMT is minus 40. You're adding $40 to the account every period. Solve for future value. And this table recaps example F, page 35. Moving from future value calculations to present value, discounting. Present value is the current value for a future amount based on a particular interest rate for a certain period of time. PV computations are called discounting. It allows you to know how much to deposit now to obtain a desired total in the future. If we take our basic future value equation and solve for PV, then you have the PV equation. As with the FV calculations, the PV interest factor is 1 over 1 plus I raised to the n. There are 4 methods of calculating the present value of a lump sum. Formula, table, calculator, Excel. As with future value, we're going to look at all 4, but we're going to focus on the calculator and Excel. Example G on page 35. Again, beginning with a lump sum of $1 to be received in 3 years at a 10% rate. Note again that the formula solution equals the PV factor from the table. Continuing example G with all 4 methods on one slide. In the calculator and Excel solutions, the future value is entered as a positive number, which means the present value solution will be negative. This can be read as, if you invest 75.13 cents today at 10% annual interest, you'll have $1 in 3 years. Example H on page 35 uses dollar amounts other than $1. In this example, you need $300 in 7 years. If you can earn 10% compounded semi-annually, how much do you need to deposit today? The semi-annual compounding requires us to match the interest rate and the number of periods. So N is equal to 7 years times 2, 14. IY is 10% divided by 2, 5%. Payment is 0, future value is 300. Solve for present value. Again, note that your solution is negative, the amount you need to invest today to have the $300. Recapping both examples G and H, this is on page 35. So far we've looked at the present value of a lump sum. Now we expand to the present value of a series of amounts, an annuity. You can use present value of an annuity computations to determine how much you need to deposit now so that you can withdraw a certain amount out of the account for a desired number of years. Again, 4 methods: formula, table, calculator, Excel. As with the computation of the future value of annuities, the sign convention is very important. In example I on page 36, you wish to withdraw $1 each year for 3 years. Your account earns 10% annually. Withdraw means income to you, an inflow, a positive cash flow. You want the future value in the account to be 0. You want to exactly exhaust the accounts with your withdrawals. Since the payment is positive and future value is 0, present value will be negative. Asking how much you need to deposit today means we're solving for the present value. All 4 solution methods are shown on the slide. When the dollar amount is equal to $1, then the formula, Excel, and calculator solutions equal the table factor. Example J expands to payment values other than $1. In example J, you want to withdraw $100 every year for 10 years, and your account earns 14%. Focus on the calculator solution. N is 10. IY is 14. Payment is 100. It's an inflow to you, so it's positive. Future value is 0. Solve for present value. So if you deposit $521.61 now at 14% interest, you can withdraw $100 each year for 10 years. Page 36, this is a recap of examples I and J. Our final look at time value of money problems involves finding the annual payment on an amortized loan. In example K on page 37, you borrow $1,000 at 6% to be repaid in 3 annual installments. The formula solution is fairly involved, so we're skipping it on this one. In this case, we're solving for payment. Future value is 0. You want to pay the loan down to 0. Present value is the amount of the loan. It's an inflow to you, so it's positive. This method can be used to solve for the required payment on any amortized loan, car, mortgage, etc. The main difference is that most amortized loans are paid off with monthly payments, meaning the interest rate and the number of periods had to be changed to monthly. This table, page 37, recaps example K. And that ends time value of money.